Today I'll be talking about atomic orbitals, the hybridization of the atomic orbitals, and the resulting geometry and bond angle of the hybridized orbital. We'll also cover sigma and pi bonds. So there are different types of atomic orbitals in atoms. The S, P, D, and F. So here I have 1s atomic orbital. It's spherical in shape. We have 2s atomic orbital. It's a little bit bigger sphere because 2s orbital is away from the nucleus. And then we have p orbitals. When the p orbital is along the x-axis, we call it the px orbital. When it's along the y-axis, we call it the py orbital, and when it's along the z-axis, we call it the pz orbital. So all the three p orbitals are of equal energy, and they're called degenerate levels. So these atomic orbitals in an atom can mix to give rise to hybrid orbitals. The hybrid orbitals can be sp or sp2 or sp3 or any other hybrid orbitals. Each of these hybrid orbitals will be of equal energy level. Let's look at an example. So in this case, these are the pr atomic orbitals of boron. You have s orbital, px, and py. So these three atomic orbitals will mix. The process is called hybridization, and this will result to give rise to three sp2 hybrid orbitals. It's right here. The arrangement of these three sp2 hybrid orbitals is based on valence shell electron pair repulsion method. And according to this method, the orbitals are placed so as to minimize the steric repulsion as well as to maximize bonding. So in case of sp3 hybrid orbitals, they will be placed in such a way that the bond angle between them is 120 degrees, and all the three orbitals are in the same plane. So it's trigonal planar structure. So let's see how sigma bonds are formed. Let's take a simple example of hydrogen molecule. So the 1s orbital of a hydrogen atom can overlap with a 1s orbital of another hydrogen atom to form a sigma bond. And the overlap between the two 1s orbitals is along the internuclear axis for a sigma bond. Let's consider another example, hydrochloric acid. Here the 1s orbital of hydrogen overlaps with the 2p orbital of chlorine to form the sigma bond. In the last example, it's an example of chlorine molecule where two chlorine atom p orbitals will overlap to form a sigma bond. Let's see how pi bonds are formed. So pi bonds are special. They are formed when two parallel p orbitals overlap laterally. Then a pi bond is formed. For example, the double bond in a carbon double bond or in a carbonyl group represents a pi bond. So let's now look at an example of boron hydride, where the sp2 orbitals, this is a hybrid sp2 orbital, overlaps with the 1s orbital of hydrogen to form a sigma bond. So each sp2 orbital can overlap with a hydrogen atom. So we have three sigma bonds in BH3. So the boron hydrogen bond is the sigma bond. So let's continue our talk about hybridization and the geometry of the resulting atomic orbitals. So I've created a nice table here. This is a list of all the key atoms that are observed in organic molecules. We have the atomic number in this column. The ground state electronic configuration is also written right here, and it's based on Aufbau's principle. The atomic orbitals that are involved in hybridization is in this column. Then we have the hybrid atomic orbitals, followed by the atomic orbital that's available for pi bond or resonance. So resonance here is in color coded in purple, and I'll talk more about it soon. So we have covered the hybridization of boron. And one thing that we need to remember is that the sp2 hybrid orbital have 33% s character, because the s orbital is split between three hybrid orbitals. So that's 1/3 is equal to 33%. Let's consider carbon atom. It has an atomic number of 6, and it will undergo hybridization in 3 different ways. So there's quite a bit of variety here. So if a s orbital and a p orbital mix, it will give rise to 2 sp hybrid orbitals. And based on the valence shell electron pair repulsion method, the 2 sp orbitals will be 180 degrees apart. And they have a 50% s character, since the one s orbital is now split. The s orbital character is split between 2 sp hybrid orbitals. The other thing that we need to remember is when the carbon is sp hybridized, it has 2 electrons in the p orbital, 1 each in py and pz. And these electrons are available for pi bonding. An example would be acetylene molecule or ethine. Let's look at when carbon atom is sp2 hybridized. In this case, s orbital and 2 p orbitals will mix to give you 3 sp2 hybrid orbitals. There will be a single electron in the pz orbital that's available for pi bond formation, as in case of ethene. sp carbon can also hybridize to give rise to 4 sp3 hybrid orbitals, and this happens when s orbitals and 3 p orbitals mix. In this case, the 4 sp3 hybrid orbitals have tetrahedral geometry. The bond angle is 109 degrees and the s character is 25%, since the s orbital is split into 4 sp3 hybrid orbitals. Nitrogen, oxygen, and sulfur are very unique. Couple things to remember. I've kind of color coded them in purple. One thing that I want to point out is whenever nitrogen, oxygen, and sulfur is sp2 hybridized, then we have a lone pair of electrons in the p orbital, and these lone pair of electrons are available for resonance. And nitrogen, oxygen, and sulfur will undergo sp2 hybridization typically when there is a double bond attached next to it. And we'll show some examples and we'll cover that topic in further detail. Nitrogen, oxygen, and sulfur can also undergo sp3 hybridization by mixing of the s orbital and 3p orbitals. In this case, there will be no lone pair of electrons in the p orbital available for resonance. So just to summarize about the sp, sp2, and sp3 hybrid orbitals, in terms of its geometry, the number of orbitals, s character, p character, as well as bond angle. It's good to memorize these facts so that you can solve the problems later on. Another fact to remember is presence of lone pair of electrons in molecules. Let's consider ammonia. In ammonia, the nitrogen atom has a lone pair of electrons. It's sp3 hybridized, but the bond angle is 107 degrees because the lone pair is going to push the NH bond a little bit closer. And so it is slightly different from the normal tetrahedral structure, which has a bond angle of 109. Let's consider the example of water. In case of water, the oxygen atom is sp3 hybridized, but it has two lone pair of electrons, and these two lone pair of electrons is going to make the water molecule a little bit different in bond angle. And the resulting bond angle in this case is 104 degrees, which is a little bit far away from 109. Now let's look at some strained molecules such as rings. Cyclopropane is an example. In this case, the bond angle is 104 degrees because of the ring strain. So these are the two factors that will reduce the bond angle from the normal bond angle. One is lone pair of electrons and other is ring strain. So let's consider a simple molecule like acetylene. It has a linear geometry. The reason is it has two sp hybridized carbon atom, and each of the carbon atom is bonded to a hydrogen atom. So the sp orbital of the carbon atom is going to overlap with the s orbital of the hydrogen atom to make a sigma bond. So we have three sigma bonds here represented in red color. In case of the carbon-carbon bond, the sp orbital of the carbon, each carbon will overlap to form the sigma bond. The pi bonds are represented in black color, and the bond angle between the sp2 orbitals is 180 degrees. Let's look at an example of boron hydride. In this case, boron is sp2 hybridized, and we have three sigma bonds represented in red color. Bond angle is 120 degrees. It's a trigonal geometry. In case of methane, this is an example of methane. The shape is tetrahedral and the bond angle is 109 degrees. There are four sigma bonds, and the carbon-hydrogen bond is formed by the overlap of the 1s orbital from hydrogen and the sp3 hybrid orbital of carbon. So let's cover some examples and learn how to identify the hybridization, the geometry, the bond angle, the number of lone pair of electrons and in which orbital they are, and the number of pi bonds. So let's start with atom number 1. In this case, this is the carbon atom right here, and it's attached to another carbon here, a nitrogen here, and an oxygen here, and it has this pi bond. So this carbon atom will be sp2 hybridized. The bond angle will be 120 degrees and it has one pi bond. Let's consider the second atom, which is the nitrogen atom. In this case, it's attached to two hydrogens and one carbon. And nitrogen has a lone pair of electrons. Now this lone pair of electrons is in the p orbital, because if you recall, anytime nitrogen, oxygen, and sulfur are next to a double bond, then the nitrogen will prefer to have the lone pair of electrons in the p orbital, and therefore this nitrogen is sp2 hybridized. And the amide bond cannot be rotated about the carbon nitrogen because of the delocalization of electrons from nitrogen into the carbonyl group. Let's consider the third atom, which is the nitrogen atom. Again, in this case, it is attached to two hydrogen and one carbon. but this carbon is not sp2 carbon. It's not attached to a double bond, and so this particular nitrogen will be sp3 hybridized. The lone pair of electrons will be in the sp3 hybrid orbital. It will have a bond angle of about 107 degrees because the lone pair of electrons is going to push the bonded pair of electrons much closer. Let's look at another atom, which is atom number 4 right here. It's nitrogen. In this case, this nitrogen is attached to hydrogen and then one carbon here and one carbon here. So the lone pair of electrons on nitrogen, since this carbon atom is a double bond, therefore the lone pair of electrons will be in the p orbital, so that there can be delocalization of electrons. And so this nitrogen is sp2 hybridized. It is planar, trigonal, and the bond angle is 120 degrees. Let's look at carbon atom 5. This carbon atom is attached to hydrogen and it's attached to another carbon, and so it's sp hybridized. The bond angle is 180 degrees, and there are 2 pi bonds. Let's look at more examples. So in case of atom 6, which is oxygen, is attached to one carbon here, one carbon here, and oxygen has 2 pair of electrons. And because it has 2 pair of electrons, in this case, both the carbon atoms right here, they are not attached to a double bond, and so oxygen is sp3 hybridized. It's tetrahedral, and it has 2 lone pair of electrons in the sp3 hybrid orbitals. Let's consider the carbon atom, which is atom 7. In this case, it's attached to a carbon here, and an oxygen here. In this case, the carbon atom is sp3 hybridized and has a bond angle of 109. It's tetrahedral. Let's consider carbon atom 8. It has a pi bond right here, and so it's sp2 hybridized with a trigonal planar structure and bond angle of 120 degrees. Let's consider carbon atom 9. It has 2 hydrogens right here and a fluorine and a carbon attached, and so it's sp3 hybridized. It's tetrahedral. In case of nitrogen, there is a lone pair of electrons in nitrogen, and it's sp2 hybridized. It's trigonal planar. It has 1 pi bond. Let's consider the example of sulfur. In sulfur, just like oxygen, it has 2 lone pair of electrons. Just have to kind of memorize that piece, that sulfur and oxygen have 2 lone pair of electrons. And now the sulfur is attached to a carbon which has a double bond right here. And so if you recall, whenever you have sulfur, oxygen, or nitrogen, which is attached to a double bond, then the lone pair of electrons on the sulfur atom will be in the p orbital, so that they can be delocalized to give greater stability to the molecule. So in this case, sulfur is sp2 hybridized. It's trigonal, and there's 1 lone pair of electrons in the p orbital and another lone pair of electrons in the sp2 hybrid orbital. Let's look at carbon atom 12. Here it's attached to 1 carbon here and 1 nitrogen here. There are 2 pi bonds here, and so this carbon is sp hybridized. It has a linear structure, and bond angle is 180 degrees. Let's consider the last example. This atom is nitrogen. Uh, it has one bond with carbon, and there are two pi bonds. So this nitrogen is sp hybridized, and the lone pair of electrons is an sp hybrid orbital. Thanks for watching. Like and subscribe.